On a sweltering summer day, people flock to rides such as log flume rides, rapids rides, and water slides. But how do these deliver the thrills? My name is Zach, and this is Engineering the Thrills. Nothing beats the heat more than water, and these water rides are very popular on the hottest days of the year. Log flumes and water slides are the two biggest draws, but how do they deliver the thrills when they're water channels with very few drops? Let's find out. But first, some history. The log flume ride is based on actual log flumes used in sawmills, transporting the logs to the mill from the site they were cut down on. This inspired the first ever log flume ride, which was El Aserradero, built in 1963 at Six Flags Over Texas. This, and most others, had a sawmill theme as a nod to their inspiration. El Aserradero was constructed by Aerodynamics, who at the time were constructing rides for Disneyland. Aero constructed almost all of the early log flumes, including this one, Le Chute at Busch Gardens, Williamsburg. So how do these rides work to deliver thrills? Well, these rides work a lot like the gutters in your home, since they're also open channels. The thing is, they are almost opposites with how much water is in the channel. Log flumes are filled to the brim, whereas water slides barely have any in them. What gives? Well, you gotta keep in mind that they're also pushing a ride vehicle. Heavy fiberglass boats versus inner tubes or foam mats, or heck, your own body. Alright, enough jibber-jabbering. Let's get to the science behind them. So, in order to figure out how these work, you need this equation, Manning's equation, which in this case is used to calculate flow velocity, is V equals K over N times R to the 2/3 power times S to the 1/2 power. V is velocity, K is a constant depending on what units you're using. 1 for SI, 1.49 for imperial. N is Manning's roughness, which is determined by the material we're using. In this case, it's fiberglass, so N would equal 0.01. R is the hydraulic radius, which is more useful than the diameter since it's an open channel, and S is the slope of the channel. If you want to calculate the flow rate, multiply this answer by the cross-sectional area A to get the flow rate Q. Hydraulic radius is given with this equation, R equals A over P, cross-sectional area over wetted perimeter. As an example, if the slope is 1/2, the width of the channel is 3 feet, and the depth of the water is 2 feet, what is the final velocity? It's calculated like this. First, calculate the hydraulic radius. 3 times 2 equals 6 feet squared. That's the area. 3 times 2 times 2 is 12 feet, the wetted perimeter. Then divide them. 6 divided by 12 is 0.5 feet. Once you have that, plug it, the slope, and the roughness into Manning's equation, giving us this. 1.49 over 0.01 times 0.5 to the 2/3 times 0.5 to the 1/2. K is 1.49, N equals 0.01, R equals 0.5, and S equals 0.5. This gives you a V of 66.37 feet per second. That's your final velocity. Hopefully this helps with calculating open channel flow. Thank you very much for watching, and I'll see you next time.